Okay, here we go. Uh, let's take a look where we are. We are, it's November 16, right? Did you get that? Yeah. So, according to the schedule, we're going to talk about sorting. And then the next lab, which is on Wednesday, there's lab today. The binary search problem is due this Friday. And then next, a week from Friday, the sorting problems are due. And so that's why I want to talk about sorting today. And then there's exam 2 on Wednesday. So I'll try to run through sorting as quickly as I can. And then maybe take some questions on exam 2. There's no surprises about exam 2. It's just going to cover everything that we've had so far in the course, excluding sorting. Right, so the topic today will not be on the exam, but binary search will be on the exam. The binary search problems are due this Friday, but the exam will have binary search, and that's this Wednesday. So sorting is the second to last topic. We're also going to talk about application development in general. Right? So let's talk about this sorting. So the first problem here is to create a function called mySort that takes a vector of integers and rearranges the elements in the vector so that they're in ascending order. And this is a basic problem. When computers were first invented, in the 50s, and they were being used to process information, this was one of the earliest problems that came about, was how do you take a sequence of values and rearrange them into the right order. So this is a sort of a early fundamental problem. And as a result, it's been studied extensively. I mean, the theory of sorting, everything's been pretty much hammered out. I mean, there's probably nothing new to learn about sorting at this point. Although I'm probably wrong about that. But what we're going to do is not look at the sophisticated sorting algorithms, which are fast. We're going to look at the simple sorting algorithms, which are slower or inefficient. So if you want to sort a large number of values and the speed at which that thing is going to run, if that's important to you, then you're not going to want to do it using the techniques that we're going to look at today. You'll use a different technique, which is more complicated, harder to understand. And yeah, so here's the assignment is just 2 problems right here. So let's go over this. So here we have the beginning of some test code. So we'll look at code as we're going through this. There we go. So the problem is to implement a function called mySort. And it takes a vector of integer. But what I'll do is I'll make this an array of integer, just to make it a little bit different. So you have a little bit more work to do on figuring this out. So we have integer a array. So it's an array of values, and it has size n. So remember, unlike vectors, arrays don't have the size information attached to them as part of the data type. Vector is a complex data type. It's a class, and it has member functions and member variables. So we can group together different kinds of information or state and have it represented by a single instance of a data type. So the array structure is not like that. So the array is a way of organizing, forcing a sequence of values to occupy memory contiguously. And the reference that we have to that data structure, A in this case, that reference, it's just a pointer into the memory, and there's no information about the size of the array, the number of elements in memory. So we have to maintain that information separately from that pointer, from that reference. So we call my sort. Well, first we create an array. Something like this. And so these are not in the correct order. We call my sort on A. And what's the size of this? 7 values. And then we'll have the test. How do we check? Well, we can use assertions for the test. We can assert that A of 0 equals -9, because these numbers will be rearranged into an ascending order. A of 1 will be -7. A of 2 will be 0. A of 3 is 1. A of 4 is 3. A of 5 is 11. And A of 6 is 100. Kind of messed that up there. There we go. So there's our test code. Remember, we're doing incremental development, which means we write a piece. We create a sequence of prototypes, runnable, testable prototypes, and converging to the end state, the end problem, the end solution. And in that process, we're also, in addition to doing incremental development, we're following a test-driven development strategy. So we write the test first, then we do the implementation. All right, so this test should fail. So it doesn't even compile. And I actually left the data type out on purpose here. So sort has no return value. So we declare it void. So what it does is it gets this A. A is actually a pointer into memory. If you look at A is a variable. It takes 4 bytes on a 32-bit machine. And it's got an integer value in it that references, that points into RAM, into memory. And that's the beginning of this array. And so we have this pointer into memory. And so we're basically operating directly on memory inside this function, where A is stored. So we're not making a copy of this array. When you have a vector, you've got to use this ampersand here to declare to the compiler that V is a reference to a vector. If you omit the ampersand, then the compiler makes a copy of v. And we're going to end up sorting a copy of v, which is then discarded when we exit the function. This is also void. So just something to think about. Maybe it's not that important to you now, but it's critically important as you go along. You have to understand what I just talked about completely, 100% thoroughly. All right. So this is failing. So the question is, what do we do? How do we rearrange these numbers to put them in the correct sequence? Well, let's just do it. Let's do it manually, you know, and just study how we do it in our heads, and then maybe use that as a way to figure out what the algorithm is. Let's do it in our heads here. I'll do it in my head. So I'll start visually looking here. I'll say, oh, here's a number. What I want to do is put the, you know, I know that in the first slot of this sequence, it's got to be the smallest number in the list, right? So I'm going to say, I just want to fill in this first spot here. I'm going to set I to 0. So I'm going to use I to reference this first location in the array. I say, okay, what am I going to put here? I'm going to have to, if something is smaller than 3, I'm going to swap 3 with that thing. So 11, is 11 smaller than 3? No. Minus 9, is that smaller than 3? Yeah, that's smaller than 3. So minus 9, well, there's 2 ways of doing this. Let me do it the easy way. I'm going to do it the easy way. I'm going to say, all right, minus 9 is smaller than 3. So let's go ahead. By the way, I got another index I'm using to keep track of what I'm looking at. I'm looking at J here is set to 2, to slots 2. And I say, well, the thing at J is smaller than the position, you know, that I'm trying to fill with the smallest value, I. So I'll swap what's at I with what's at J. So 3, oh sorry, that's minus 9. So I'm going to put minus 9 there. 11 stays where it is. And 3 goes to where J is. You know, that 100 is a problem. It's going to throw me off. I'm going to change that to 99. It's just formatting. I just don't want to deal with that extra digit. So, you know, we swapped the value at I with the value at J. And now what I'm going to show you here is the result of that swap. That's the result of the swap. Now also keep in mind that, and I'll put a space like this as well to show a break. I still have got I here and J there, and we just swapped those. Now, what are we doing? Let's not forget what we're doing. We're trying to set the value at I to what it's supposed to be, which is it's the first value in the sequence. We want to set it to the smallest number. We found a number that's smaller than what's at I, that's minus 9. And so we swapped I and J. What's at I with what's at J. Now we're going to move J forward. So, okay, 99, we're going to compare what's at I with what's at J. Well, what's at I is smaller than what's at J. See, you know, and you just go through here. See, even minus 7 is bigger than minus 9. So we're scanning. We said when we started out in the beginning here, we said we're gonna put in the first slot the smallest number. So we have to scan across the list, and each time we find a smaller number, we're going to swap it into that spot. Now we're done with this. So we got that spot. We got spot 0 done. So now let's go ahead and look at spot 1, right, the second slot. Let's get in there the next smallest value. So we're going to want to look at everything except the one we already did, because we know that's smaller than everything else. That's why we start at I here, and actually we put J on looking at the same spot. Well, actually we don't have to do that. We can set J to here. We can start J there for like. And so J is like it's like our eyeball going across the rest of the vector, looking for the next smallest value to swap into that position I. You just have to think about how you do it mentally. Just to figure it out how you're going to mentally do it manually, and then you just observe what that algorithm is. Also, now 3. Is 3 less than 11? Yeah, 3 is less than 11. We're going to swap that. We're going to put 3 here. We're going to put 11 there. And let's keep going. Is 3 less than 99? Yeah. No reason to put no, so we advance J. Is 3 less than 0? And no, 3 is not less than 0. So we're going to swap what's at J with what's at I. See that? And we advance J. J is now, the position that J points to contains a 1. Is 1 less than 0? No. One more to go, -7. Is -7 less than 0? Yeah. Oh, we found a smaller value. We've got to swap it in there. So this will be -7 now. See that? And then J, of course, J goes off the end here, and we say, oh, that's it. We're finished. So that means we've finished the second slot. So we've done the first and second slots. So now we're going to do the next slot, which is right there. So now slot 3, I equals 2. No, it's slot 2. It's a position 2. The third position. I know that's confusing. So we do the same thing. Is 99 less than 11? No. Is 3 less than 11? Yeah. Let's put the 11 there. I put the 3 over here. All right. Now J is at 1. Is 3 less than 1? It is. All right, we got a new smaller number. Let's put that 1 in there. Keep going. Is 0 less than 1? It is. Yeah, I got a good example this time. Sometimes I have dud examples. And now I goes past the end of the array, and we finished filling in the third slot. Now what we do is we advance I to the fourth slot, slot 3. Start the process over. Is 11 less than 99? It is. That's 11. We swapped 11 with 99. Advance J. Is 3 less than 11? It is. We're going to swap 11 with 3. Advance J. Is 1 less than 3? It is. We're going to swap 3 with 1. Advance J. Oh, J is too big. Done. Let's keep going. Let's advance I. That's to the next spot, the next slot that we need to get the next smallest number. set j to the next value, 11. Is 11 less than 99? It is. Let's swap. Oops, that was not working. Advance j. Is 3 less than 11? It is. Push j farther. Oh, j's past the end of the array. Now let's advance I. And reset j back to the value 1 past I. Is 11 less than 99? It is. Okay, swap. Don't get sloppy right now. Don't cut it quick and jump into the algorithm. Finishing up at the end, this is where you can get one off. So go slowly at this point. This is the point where you slow up and make sure you get it right. So we just swapped the values at I and j. And then we advance j. Okay? We're slowing up here. We're going to get this. J is past the end, so we're done. What's in I is good. And then we advance I. Now hold on there. I. We want to find the next smallest value, which comes after I. Well, I is the last spot, right? So there's nothing smaller than, there's nothing else, there's no other smaller candidate, so we're done. So when I goes into the last position, there's nothing else to do. That's it. Can you code that up? Can you write that out, what we just did? You can do it. How long do you think it would take you to do that? A while, yeah. But this is the kind of exercise that you should do, okay? And if you're a math major, just memorize the algorithm if you want to, okay? If you want to be a programmer or you want to study computer science or computer engineering, you got to think this out. Don't just memorize the solution. It's not going to help. You have to go, oh, I see what he did. He developed a mental procedure. He figured out how to do it step by step. He used an example. And now I am on my own going to code this up. You got to do that. Otherwise, you'll sink later on. You'll have trouble later on. Because you won't have gone through that mental exercise to figure that out on your own. And then when you get to more complicated algorithms, you're going to have trouble. And then when you get hired and you got a job and you got to do this for a job, then you're not going to be able to do it. So take the time to try this out on your own, figuring it out on your own without referring to your notes. It's very useful. And it's going to take you, if it takes a whole day, that's great. Take 8 hours. Spend 8 hours on this. It'll be more worth it to you than anything I can imagine. I mean, if you're going to be a computing major. Even if you're going to be a math major, it might be worth it to you also. I was a math major. Here's an example. It was worth it to me. All right, so that's enough of that business. So let's code it up. All right, what do we do? Well, think about how we did this. The thing that was driving the process was I. And I started at 0, and it kept incrementing and going larger. So we've got a loop there. And I was some kind of limit, right? We had to stop somewhere. Let's be fuzzy on that for now. And then we had to increment I. And then we got to do something in there, right? So there it is. That's my first take, all right? You can't just type it all out, right? You got to break it down into steps. That's what I mean by incremental development. That's what I see right off the bat here. That's what we did. You know, we used J, but J was sort of, you know, I was the driver, I was the elephant, and, you know, J was the monkey running around. You know, every time I took a step, J had to run across the rest of the list. So J is being controlled in the inner loop. Right? I is in the outer loop. And where did I stop anyway? Well, we figured it out here, right? When I reached the end of the array, n, you know, once it hit n minus 1, that was good. Like, remember, this array, let's think about that for a second. This array's got 7 elements in it. The I here is 6, right? So n is 7. The size of the array, n is 7. When I hit 6, we're done. So that means we only want to do the loop when I is less than 6. When I hit 6, we're done. So we need I to be less than n minus 1. You see that? So there's that. You got to think carefully here because you've got the one-off issue, the one-off problem. You got to slow up and think this one out when you hit this spot here. Don't be one-off. All right. And then, so we got the outer loop. Now the inner loop is going to be controlled by J. Oh, J0, is that right? Doubt. Problem.
1.
No, 1? J, we said J. Huh? I plus 1, thank you. I plus 1. We don't need, if we start at the beginning, we're going to find a small number, right? J just starts at I plus 1 and goes to the end. So that part was a little tricky. What about J here? We know that J is going to be, oh, what am I doing? I know I'm going to be incrementing J there. I'm just going to type that out. What is the limit for J? Is it n minus 1, just like I? Huh? N. Because J, we want J to hit n minus 1. We want J to hit, look, here J is 6, right? We want J to be 6. Well, this is not a good example. This one here is a good one here. In this step here, look, we want J to hit 6 because, you know, 11 is less than 99. Well, I mean, supposing that I were to be here. And we want to swap these. So we have to let J hit 6. We have to let J hit n minus 1. So that means we want J to be strictly less than n. So we allow n minus 1, but n we don't allow. I mean, you could do it like this, right? It's just that you don't see that. You don't see that. Counting starts at 0 in the computers. Inside the hardware, counting starts at 0 on a hardware level. And so if you work at the hardware, that's why all these languages evolved out of the hardware. Now, they didn't invent computer programs and then build a machine that would run them. They didn't do that. They built machines that were just pure hardware. And then as the hardware evolved, the languages developed out of that. And in hardware, counting starts at 0. All right. And that's why we get these funny things that work differently than the way we think. And I just had this funny thought. What happened if we, as a society, changed and started teaching our children to start counting from 0? Do you think they'd be better programmers later on? I wonder. First time I ever had that thought. So there's the loop. So what are we doing here? We're comparing, what's at I with what's at J. So if A of I is greater than A of J, then we've got a problem. Then we want to swap the values at I and j. Did we look at swapping last time? No, we didn't do that. There is a swap function here in the system.
I think you told us not to use it.
Yeah.
Is that what I did?
Yeah.
Don't use swap? I said don't use swap?
Yeah, because we had to do it by
A temporary variable.
Yeah. Temporary.
Yeah. Well, you only need to do that exercise once. Okay.
No more temporary.
Huh? So here, I mean, it's good. If you don't remember how to swap, then you try to implement swap here. You just need a temporary variable and you move things around. So that's what the swap function does. If you dig in there and look at it, they're going to create a temporary variable. That's it right there. Look, that's all there is to it. Isn't that amazing? That's what I think. I mean, that's going to fail here.
Is it? It is. The last insert.
99.
No, you put 906.
Huh? Oh, thank you. Look at that. Thank you very much.
Can it work?
I wouldn't have felt like victory, you know, it wouldn't have worked. Huh?
Can it work instead of doing AI greater than AJ? Can we put AJ is less than AI?
Yeah, you can do that. Yeah.
No, we need a semicolon.
You can do that. If AJ is less than AI. If this makes more sense to your mind, do it that way, because that's the readability principle. Because the two of these are equal in terms of speed, execution speed. And execution speed matters in sorting, but it doesn't matter that much. And I mean, depending on what you're doing. And so what you want to do is make it more readable. If this is more readable for you, and make it easier for you to reason over, then do it this way. And the order here doesn't matter either. This could be AJ, AI.
I think we need a.
Is this going to work?
No, we need a semicolon at the end of the brackets.
At where?
The braces. At the end of the braces. For the.
Like down there? Oh yeah, I need one here. Thank you. Thank you. That is. Actually, I'm missing two braces.
And then a semicolon at the end of the braces.
A semicolon after this one?
No, you declare where you declare the rate. Yeah.
Oh yeah. That compiled though, didn't it? Did this compile? What the heck? Did that? I thought we compiled it.
Nah.
Oh, you're right. That's great. Thank you. You're a human compiler. That's it. You think we got it?
Then we need a class for it?
What?
For the swap?
What?
For the swap? Don't we need like a.
Oh, an include?
Yeah.
I'm not sure. No, because it compiled, see?
Oh, okay.
But it may not compile on your system. In that case, you need to include
It compiles. What class is it?
compiled on yours.
Yeah, it compiles in C9 with swap without a class for swap.
If it doesn't compile, then I think it's going to be in the algorithm header.
For mine, it compiled and ran.
I think you don't need this. I think you don't need that, but just in case, let's see what it says here. The internet. Let's see what the internet says. Algorithm. Oh, in C++99, this version of C++99, it requires this to be in the algorithm header. In C++ 11, it's in the utility header. But as you can see, we didn't need it. It does, it got, there's some different compilers, but you may have a compiler that wouldn't build this code, depending on the version of C++ it implements. You'd have to include one of these headers. Yeah.
On the side, different question, but for this problem here, could you do this without doing a swap, but instead pushing back the rest of the variables, or the rest of the numbers, I mean? So for example, on the second one, you push each one and bump them all over.
Yeah, there's another, that's a very good question. That's a very good observation. Let me tell you, I'm showing you one sort, that's it. I'm showing you one sort algorithm. There are many. And the algorithm you're describing is one of the big ones that people implement. It sounds like bubble sort, where you're kind of swapping things in a line. And there is a sorting routine called bubble sort, which sounds to me like where you're headed with your thinking. So you can look at that bubble sort. Now this one here, this is called, it's either insertion sort or selection sort. They've named these things. I mean, these things have been extensively studied. And I showed you the sort routine that has the fewest lines of code that I've ever seen. I mean, look at that. It's essentially 3 lines of code, right? 3 lines of code. But the swap, I mean, the swap is a little wasteful. So another way to do it is have a third variable, say k, and k marks the smallest value that you've seen so far. And then when j gets past the end of the array, you swap I with j. So you only do one swap. Here we're doing multiple swaps. The benefit of doing multiple swaps here is that we don't need to introduce a third variable. So it keeps the variable count down. It makes it more readable.
But it's more efficient with the third variable.
It's more efficient with the third variable, a little more, not significantly more, just a little bit more. So readability wins out in my mind.
So in the test, it would be better to use the third variable or swap?
In this particular example, I don't think it matters. I don't think third variable matters. Maybe it's a little bit faster. It depends on what you're going to use it for, I guess. But you wouldn't use this to do real problems. I mean, unless it was a little problem. You're going to want to use merge sort, or quick sort, or heap sort. Those are the 3 that come to mind. And the ones I think, there's a sorting routine built into the language. I mean, through the standard library, that the implementers probably use quicksort on. There's an algorithm called quicksort. On the average, quicksort is faster than all the others. But there are situations where quicksort deteriorates and becomes very slow, but those are rare. Anyway, that's sorting. That problem has been hammered on for ages. But we didn't run it yet. Let's see it. Let's feel that success. There it is. What time is it? 1:15. Close that out. Comparison. Oh, here's the algorithm header here. It has a sort routine built in. And this is how you would sort, using the function that we implemented there. And you'll see how much faster it is to sort. Now, I can show you this part of the assignment, or else I can answer questions about the exam coming up. Let me start by answering questions about the test. And I can't imagine there's nothing really to answer, because there's nothing new that you've seen everything. But yeah, back there.
Yeah, so it's cumulative, or is it just like
Cumulative, yeah. Yeah, you gotta know everything.
So it's up from.
I don't think I have any problems with what does this code print? I don't think I have that question on the exam. But that will be on the final. Huh? It'll look like binary search is going to be on there. Binary search will be on there. Where's exam 2? Look, it'll look like the old exams merged together, by the way. So here's spring. Bean jar. I give you this code, and then I say, draw the UML class diagram. I may give you the class diagram and ask you to, write out the definition, the declaration here. I may go the other direction. And then, provide an implementation of the bean constructor. I'm going to do this really fast because this is like memorization. This is hard. If I had my way, I wouldn't cover classes in this course. I would forget classes and I would cover pointers instead. But, and focus on arrays and algorithms. But that's, I got to work with other people, and, this was the group decision that we're going to cover classes. So that's it. Anyway, so let's take a look at that. So we got to do classes. And this is what the problem looks like here. I'm just going to do a quick review. And I said, implement the constructor. That's problem 1 is the UML class diagram, right? And then problem 2 is implement the constructor. Provide an implementation of the bean jar constructor. All right, I'm going to show you an answer that gets 100% credit, okay? Wait a minute. You know what? I got to put that down here. I need to do this. So you got to write this out, actually. That's max. All right, that's the answer to the first one.
Double colons. Yeah.
Double colons? Oh, yeah. No, I'll tell you right now, if you left that out, that would be okay. For me, and when I grade the test. I mean, it should be, put it in there. Yeah, because if you take the class of another professor, like 202, you might lose points on that. I don't know what they enforce. So play it safe, you can do this. But actually, sometimes I give the function signature inside here, and that makes it easier. Then you don't have to do all this. I got to tell you, if you did this, if I saw that on the exam, if I saw that, I would give full credit for that. And actually, if I had to redo this test, maybe I would put that, function declaration right in there. So you didn't have to write it out. I want you to understand the concept here of what's going on. And, this variable, this max beans, this broader scope. This is the locally scoped max beans. That's the parameter for the function. So there's the same name that point to 2 different memory locations. So you have to qualify the first name with this to tell the compiler that it's not the locally scoped, function parameter, it's the member variable max beans. That's the hard part about this, right? To get what I just said. And I'm sure that a lot of you don't understand that yet. And it takes a while to sink in. All right. And you just go down there. I mean, we've seen this. We've already done that. All of these. Test code for add beans. Which one is that? That's 6. So say 6 is test code for the add beans function. So you need to create a bean jar. With 50 beans in it. And then all right. So remember, add beans returns true or false. We want, this is a good thing. And then we could throw this in there, but I gotta say, if you left this out, it wouldn't bother me, but this is get beans, right? It's up here, get beans. Just to make sure that that works. Now you should have that in there. And then we're gonna add 50. But that's not possible. So that's gonna be false. The value in the bean jar should remain the same. We should have the same number of beans in the jar. So there it is. That's a nice block of test code. If you happen to, these, you really should have these in there. I think you'll need to have these in there. If you didn't have this one and this one, you would get partial credit. But this is essential. You need to create an instance of bean jar, the first line. You need that because then you need to do the test with it. And the test involves this dot notation where you have that variable which refers to the instance of the bean jar class, dot, and followed by the function and the function arguments. And we're all inside of an assert statement. So this is, we've done a lot of automated test code writing in the class so far. So this, I always have one problem where I ask for test code. There's always one. I've never given more than one problem with test code. Yeah.
I just wondering how long does it take since you're adding the
Yeah,
tests?
it's going to be a little on the long side. Well, look at this test, exam 2. Now I asked about the integer class. I'm not going to ask you on Wednesday to look at 2 classes, only 1 class. Okay, so you wouldn't get a second class. All right, so it'll lighten up a little bit. And I wouldn't ask so much, like maybe I wouldn't, that's not too bad right there. I mean, I already wrote the test, but I don't remember what I put on there. But I tried to ease up a little bit to make room for the other problems.
Is there extra credit to it?
I think I put an extra credit on there. I think I did, but I can't promise that. I don't want to be made a liar. I think I put one on there. So that's the half of the exam. Here's the other half. I give you these function declarations, and you need to implement them. Are identical. You've had that in an assignment. Min value. Implement these. Let me do this one really fast, okay? Just to get you warmed up. What do? Here's the question. You don't need to duplicate that function declaration. You can omit that. This is the answer. Find the minimum value in a vector v and return its position, or return the value. Return the value, not the position of that value. Return the smallest value in v. So you need a loop. And v dot size, the size of an array. You need to memorize that. And then you've got to keep track of the smallest number you've seen so far. let's call it, x. This is a little tricky, isn't it? Well, x is not a good one.
Min?
Yeah, or smallest. Min is good. The name of the function is min value, right?
Yeah.
So I think min is good because it keeps that name. And then if a of I is less than min, then min is a of I.
Where would be v of I?
Oh, yeah, v. No, we're just trying to vector v. And then the very last thing we do is what?
Return
Yeah.
v of I.
Well, not v of I,
Yeah.
min. Right. So that was a little tough, I guess. For me, I mean, it's not tough, but. So that would be the answer. You don't need to rewrite this part. I give it to you right there. Just give the implementation. Is lucky. Write test code. Write a program that implements guess the number game. That's like the binary search. And you're going to have to do binary search. Count negatives. Search. So this is linear search. So the values in V are not in order. So you can't use binary search. Binary search only works if the values are in order. Here is binary search. Now V, we're telling you in advance that V, the values in V are in ascending sequence or descending. Did I say ascend? I said strictly increasing. No extra credit there. Okay. So that's the overview. Anything? Yeah.
So the test on Wednesday is going to be like half of 2 and half of 3.
Yeah, exactly. Half of 2 and half of 3.
I have a question.
Yeah, almost everybody will finish well before the end of the testing period. Guarantee it. We're not going to be all sitting there up to the last minute. It doesn't happen. I might get 2 students, 3 at the most. All right. You want me to do the other thing for the lab so you see that, or do you want to just call it quits? What are we working on? This one here.
What is it?
It's this comparison. It's not too bad.
Can you go?
Maybe 1,000, 100,000 might not be big enough. You might have to do 200,000. See a difference. This is fun to do this, but we can always do it later. But there won't be time to do it before the deadline for this assignment. Yeah.
I have a question from the previous attempts. It's a test from the previous attempts. It's the second one. The winter.
Spring or winter? Which one? Fraction?
Yeah. You saw.
Simplify?
Yeah.
That one? So, fractions, look at the argument. Look at the parameters to the fraction constructor. We pass in a numerator and a denominator. Like numerator is 2. Denominator is 4, right? So 2 over 4, that's a fraction. But that can be simplified to 1 over 2. And so we call this function simplify to change the internal representation of the fraction to its simplified form. So how do you do that?
See if it's mod remainder 0.
What's that?
If you mod, like, if the numerator and denominator can both be, like, mod by 2 equals 0, then they can both be.
Yeah, then you can take the 2 out, right? Yeah, this was a good problem. I think I made this an extra credit problem at one point. Here it's required. So how do you simplify? Let's look at it. We can do it pretty quickly here. Yeah, you have to use mod in a loop, I think. Just to simplify things for you. That's what we're looking at. We create an instance of fraction, and then we call it simplify. And look, it doesn't return a value. It's not const. All right, so we want to take out all the common divisors from the numerator and denominator. So we got a loop here. And we have to use, well, you know, we'll use the n, we'll say. We'll start at 2. And if, you know, I'm not going through my thinking process here, so I don't have time for that. If, you know, it is a hard problem. If, let's think about it for a minute. So we have to just use your mind and think, all right, what happens? I've got a fraction. What I need to do is find the common divisors. So 2 over 4, there's a common divisor of 2. So I got to take a 2 out of the 4 and a 2 out of the 2. That gives me 1 over 2. That's a simple one. How about, you know, 27 over 9? There's a common divisor 3. We take that out. Now it's 9 divided by 3. Oh, but 3 is yet again a common divisor. So you can take it out twice. So 9 over 3 reduces to 3 over 1. Well, then we're done, right? So we don't want to, if we try to take out a 2, we don't want to stop by only trying once. We want to try repeatedly. So that's why I've got this here as a kind of an infinite loop there, but probably it'll be something like, well, n is less than, you know, numerator or something like that. So if if numerator mod n is 0 and denominator mod n is 0, then we're good to take that out. Then numerator divide equals n. Same with the denominator.
Is that the right divide slash?
I think it is. Is it? Maybe not. Maybe it's that one. Yeah, I can't even remember.
It looks so similar.
I can't even remember. Can you believe it? Who knows?
Google knows.
Look at this. I'm getting older. Well, thank God there's an internet. Oh my gosh.
Divide operators.
I've been doing this all my life. I can't remember that. You know, let me think for a sec, because I know the escaping is backslash.
It's that one.
So it's probably this one, right?
Divided. The one with the question mark.
You see it?
Yeah, right there.
There it is. Yeah, forward slash. Yeah, it's that one. So, So else increment the n. That'll work. If you want this to run a little faster, you could go like this. Denominator. There we go. Now it'll run a little faster that way, because I could give you 2 over 4 or 4 over 2. So which one is smaller, the numerator or the denominator? So that'll be the limiting number. So we don't know which one is going to be smaller, so we could do. But this is not necessary either. You know, just one of them would have been good enough, but maybe this one is cleaner. So there's the solution right there. I know that's a hard one, so that's why you asked it, because that's a hard one. And I think that there were people that got that in this exam, but that was hard. That was a hard one. That I think most students did not get that one. That one there. So I think that if I put that on this exam coming up, I would make it extra credit. I think. I'm pretty sure. Yeah. Ampersand means and. Double ampersand means and. If it's one, that's called, you know, if I had more time, I could do this kind of stuff. Double ampersand is called logical and. This is a bitwise and. Bitwise. So what it does is, if you look at two numbers, you know, if you've got if A equals that, and B equals that, then A and B equals, you got to look at the two bits, 0 and 1. What's that? 0. 0 and 1, 0. It has to be 1 and 1 to get a 1. So 0 is false, 1 is true. So if I say it's sunny outside and it's snowing, I just made a single statement. Is that statement true or false? It's false because one of the substatements is false. You know, it is sunny outside is true. And it is snowing. Well, that's the false part. So for an and operation to be true as a whole, both operands have to be true. So both of these have to be true. And then we have 0, 0, 0, 0, 0, 0, 0, 1. That's called arithmetic and or bitwise and. I think they call it arithmetic and. Is that what they call it? Well, anyways. The same with or. You know, or would have been different. That's a bitwise or versus this is the logical or. Now, see, if we did this, A and B, right? Well, the system interprets these both as true. Everything that's non-zero is interpreted as true. And so the result gives you the same. In this case, the result is the same. But let me show you a problem. Watch this. Let's suppose I made that 0, and I made that 0, okay? That means A bitwise and B gives me a string of zeros, which is false. See that? And this is an example where the value represented by A in memory is interpreted as true. The value represented by B is also true, and A, bitwise and B gives us zeros, that would be a value interpreted as false. But in fact, if you ran this operation, you would see that the result would be true. So here's an example where bitwise and logical and are different. Now, you only have to worry about this in this language, C and C++. In the other more modern languages, you're not going to be able to, if you declare an A and assign it to this bit sequence, it's going to be a bit sequence. You can't make it look like a logical value anymore. So Java, C#, they wouldn't accept it. You couldn't do this in those languages. You can do it in a scripting language that has what's called loose type checking. But I don't, we're getting beyond the top, our scope of our course here. Yeah.
In the if statement,
Yeah.
the and there, is that
The if statement down here?
like when you have the and, it's like spelled out?
Oh, yeah. I think the newer versions of the language accept that.
But C++ does not.
Yeah. If you put and on the test, I would give it to you. Yeah.
What version of C++ are we using?
You can use any version you want.
Yeah.
Because the syntax that we're using, it goes way back into the past. Like and is not an older, your compiler might not take that. But I will take that on the test.
Just because I look online and I see like different sections or different stuff for different versions of C++, so I was just wondering.
Just say that again.
Because if I have to look online for something that I'm not too sure of, like some syntax or something like that, and it'll say different stuff for different versions of C++.
Yeah, yeah. Well, the safest thing to do is to use the oldest version. That's the most portable. That'll run everywhere. The newer versions, you're going to be careful about. They give you better readability, but if you're concerned about your code building or compiling in other systems, in other environments, then you might not want to use the new features. I guess that's it then.